Let's take a look at this one. What we've got is an 8-volt power source, and we've got a bunch of resistors here. And the first thing we've got to do is we've got to figure out how we're going to combine these. Because again, 8 volts is between that wire there and this wire here. It's not the voltage across any one resistor. So we actually have to combine this a little bit. We have to simplify this a little bit. Now, looking at this, hey, these look in parallel. Nope, because see, that end of the 6 ohm and that end of the 2 ohm are not connected together. So we have to keep looking. This is definitely in series. Any current that goes through the 2 ohm has to go through the 3 ohm. So I'm going to connect those. I'm going to replace those with a series resistor. And that series resistance, just the sum of the two. So that's going to be 5 ohms. 5 ohms there, 6 ohms there. This is a good time for me to actually start writing these down. R, I, V, and they said that these are light bulbs, so we're going to want to find the power in these things. Okay, so let me just write these down. 4, 6, 2, and 3. And now I've got a new one, 5. So I'm going to write that in there. And remember, series, same current as each other, and the same current as this. Okay, so when we work backwards, we can use that. Okay, now we have 5 ohm and 6 ohm in parallel. So we do inverse of 5 plus inverse of 6. And then we do the inverse of that sum. Oops, I've got a negative in there for some reason. Inverse of 5 plus inverse of 6. And then I do inverse of that. And I get 2.727. Okay, so I'm going to redraw that circuit. And what I'm doing is I'm replacing those parallel, same delta V. And this is 2.727 repeating. I'm just going to call it 2.73 ohms there. And we see now we've got that. Let's put that in here. I'm going to need another row here. And now I can see that those two are in series. So I can series, same I. Whatever goes through one goes through the other. So then my final simplified R equivalent for the whole thing is going to be 2.73 plus 4 is 6.73 ohms. And I'm going to put a new line there. What I've got is 8 volts across that 6.73 ohm resistor. That's good because I know that that voltage is directly across there. That's the potential difference across the resistance. So I can use Ohm's law, V over R. 8 divided by 6.73 gives me 1.19 amps. Okay, so that's how much current is going through there. Now remember, I got this from 2 series resistors. So whatever current's coming out of here has to go through there and there. So I can use those 1.19 amps, 1.19 amps. Just drawing the arrows to show where I got it. Okay, now let's come over here. Let's figure out the power. The power is going to be V times I, 8 times 1.19. For the whole circuit, that ends up being 9.52. 9.52 watts. That's really the power delivered by the 8 volt power supply. But it's also going to be the power consumed by the equivalent resistance. That's really what that means there. So 9.52 watts is delivered by the 8, or produced by the 8 volt power supply, and consumed or dissipated by the equivalent resistance. Now what we can do now is we have I and R there, and we can multiply those out. Let's see how that goes. 4 times 1.19 is going to be the voltage difference across, potential difference across the 4 ohm resistor, right? Same current, 1.19 times 4. And now let's do 1.19 times 2.73 will give me the voltage across the 2.73 equivalent resistance, which was I'm going to round a whole lot here, 3.25. Power, we could do V times I, we could do I squared R, V squared over R. Since I've got V in there already, I'm just going to do V times I, 3.87 watts. Up here, 1.19 times 4.76 is 5.66 watts. Now notice two things. The delta V across the 4 ohm resistor plus the delta V across the 2.73, 7, they add up to 8. Again, there's some rounding issues there, but they add up to 8. And the power the power delivered by the 8-volt power supply is dissipated by these two here. Okay. Now we work backwards again. This 2.73 came from 2 parallel resistors. So if we look at the voltage difference between there and there is the same as the voltage difference between there and there. So the voltage difference across each of these is the same as the voltage difference across 2.73. So what I can do is I can say, oh, the 6 and the 5 both have that same voltage difference as the equivalent that they were replaced by. Okay. And I just keep working with that. And what I'm going to do is speed this up so I can get the same process. So, okay, once I get the currents for the 6 and the 5, okay, I know that the current through the 5 is the same as the current through there, and then I can find all the voltages and power. So I'm going to do that right now so you don't have to watch me plugging stuff into a calculator. I am going to do that myself right now. Okay, now let's take a look. Let's see what we've got here. First of all, let's check, does this make sense? Kirchhoff's voltage law says any loop, the total delta V around that loop should be 0. So here, if I go here around this inner loop, or this left loop, plus 8 minus the voltage across the 6 ohm, minus 3.25, minus the voltage across the 4 ohm, 4.76, should equal 0. 8 minus 3.25 minus 4.76 is approximately 0. So that checks. Let's go on this outer loop. We could even do this loop here if we want, but let's do this one. Plus 8 minus the voltage across there, 1.3, minus the voltage across there, 1.95, minus the voltage across there, 3.25, and that should end up with 7.1. That should end up right, okay? 2, 3, and the 4. That looks good. Okay, so Kirchhoff's voltage law works. Let's see if Kirchhoff's current law works. Let's take this as the current into this node. That current plus that current has to equal that current. So the 6 ohm resistor's current, 0.546, let me write it down, 5416, plus the 3 ohms current, plus 0.65, minus that 4 ohm, minus 1.19, equals 0. I'm going to put a question mark. Well, that's 1.19 minus 1.19 is 0. So that checks. So this looks like we've done a good job on that. Now let's look at the power. The biggest power dissipation is here in the 4 ohm resistor. I'm not counting this. This is an equivalent, right? But out of the individual first four light bulbs, again, these resistors are supposed to be light bulbs, this 4 ohm, ends up having the greatest power consumption. And it sort of makes sense. You've got the current, this current here is the same as the current coming out of the battery. Then it's split up here into 2 branches. So it's sort of, intuitively it seems like that would be, as long as this isn't a really low resistance, you'd think it's going to have the most current, maybe it'll have the greatest power, and of course it does, ends up having. One big thing is this, remember power is related to I squared R. So the fact that this has more current than the rest of these, it has this current plus this current combined going through it, that ends up being a really, really big factor. High current means high power dissipated. So we've got that. the total there, 7, 8.5, 9.5. Yeah, so it ends up being about 9.52 total power dissipated.